Hello students, today we are going to start our syllabus of class 10. We are going to start with the first chapter, that is real numbers. We have studied many types of numbers till date in previous classes. First of all, in this chapter we will have a look over types of numbers which we have studied in the lower classes. First of all, we have studied natural numbers. The set of natural numbers is denoted by capital N. The natural numbers were initially used for the counting purpose. Numbers 1, 2, 3 and so on are called as natural numbers. The second type of numbers is whole numbers. The set of whole numbers is denoted by W. The set of numbers that include 0 and the complete set of natural numbers is called as whole numbers. The numbers 0, 1, 2, 3 and so on are called as whole numbers. Remember that the number 0 was invented by great Indian mathematician Aryabhatta. Let us come to the third type of the numbers. The third type of the numbers is integers. Integers are generally denoted by capital I or Z. Z comes from German word Zahlen, which means to count. Integers are the set of numbers which includes 0, natural numbers and the negatives of all the natural numbers. The numbers from negative infinity to -3, -2, -1, 0, 1, 2, 3 and so on are called as integers. The fourth type of the numbers is rational numbers, which is denoted by Q. Q stands for quotient, that is division of two numbers. Rational numbers are any numbers that can be expressed in the form A upon B, where A and B are integers and the denominator B should not be equal to 0. Some examples of rational numbers can be given as follows. 3 upon 7. Here numerator 3 as well as denominator 7 both are integers. Next one, minus 5 upon 4. Here minus 5 as well as 4 both are integers, and very important thing is denominator is non-zero. Next, let us take number 6. We know that 6 is integer, natural number as well as whole number, but 6 can be also written in the form of A upon B, like 6 upon 1, where 6 and 1 both of them are integers. So 6 is also a rational number. 0 can be written as 0 upon 2 or by taking any non-zero denominator. So 0 is also a rational number. There is no condition on the numerator. Numerator can be 0, but denominator should be strictly non-zero. Next number, 0.76. It is a decimal number. This number can be written as 76 upon 100, where 76 and 100 both are integers. So 0.76 is also a rational number. Minus 1.33 recurring. This can be written as 4 upon 3 and so on. So till now we can say that all the natural numbers, whole numbers and integers are rational numbers, as they can be expressed in the form A upon B. We can simply take denominator 1 and every natural number, whole number or integer can be written in the form of a rational number. Next one, we'll see a remark. Rational numbers can be always expressed by using terminating decimals or repeating or recurring decimals. That is, a rational number can have terminating decimal expansion or non-terminating repeating decimal expansion. So from this we come to know that a rational number can have only two types of decimal expansions. Either it can be terminating, or if it is not terminating, then it will have recurring decimal expansion. We can see it in details. For terminating decimals are decimals that contain finite number of digits whose decimal expansion is ending somewhere. For example, 36.8, 0.125, 4.5, etc. Repeating decimals. The repeating decimals we can say also as non-terminating repeating decimals. They contain an infinite number of digits, and this decimal expansion of such kind of numbers do not end. Some examples of repeating decimal expansions: 0.333 and so on. 1.9 recurring. 7.689, 689, 689. Here in the last example we can see that a particular group of numbers 689 is repeating continuously. The next type of numbers is irrational numbers. The numbers which cannot be written in the form a upon b, where a and b are integers and b is not equal to 0, are called as irrational numbers. We can say that the numbers which cannot be written in the form of a fraction are called as irrational numbers. Irrational numbers are non-terminating, non-repeating decimals. The decimals that go on forever without repeating a particular number or a group of numbers. Here we see some examples of irrational numbers. Before studying the examples, one thing should be very clear in your mind, that if a decimal number has non-terminating and non-repeating decimal expansion, we can say that it is an irrational number. Let us see the first example. 0.12312341235. In this example, not a particular number or not a group of numbers is repeating continuously. So this number is irrational. Next example, 45.86745,893. In this number also, in decimal part, we can see that not a particular number or a group of numbers is repeating. That's why this is also an irrational number. The next example is of pi. We all know what exactly is the pi. Pi is the ratio of circumference of a circle to its diameter, and that ratio approximately comes equal to 3.14159 and so on. Normally, for calculations, we take value of pi as 22 upon 7. So someone may say that pi is a rational number, but remember that the actual value of pi is 3.14159 and so on. 22 upon 7 is the approximate value of pi which we take for sake of calculations. As you can see in the decimal expansion of the value of pi, the numbers are non-terminating and non-recurring. It is an irrational number. In the same way, we have one more number like pi, which is e. The approximate value of e is given by 2.7183 and so on, where no particular number or a group of numbers is repeating. That's why e is also an irrational number. The next example is square root 2. If we find the value of square root 2 by using long division method, which we have studied in class 8, we will find the value of square root 2 is 1.4141352624 and so on. Here we can see that no particular group or a particular number is repeating in the decimal expansion of the number square root 2. That's why square root 2 is also an irrational number. In the same way, we can say that square root of any positive number which is not a perfect square is an irrational number. For example, we can say square root 3, square root 5, square root 7, square root 8. All these are irrational numbers. Whereas square root 1, square root 4, square root 9, square root 16, all these are rational numbers because we can find their square roots. Similarly, cube root of a number which is not a perfect cube is also an irrational number. For example, cube root of 2, cube root of 3, these are some examples of irrational numbers. Now let us discuss the real numbers, which is our today's topic. What are the real numbers? Now, the real numbers consist all the rational as well as irrational numbers. Means we can say that all the rational numbers and irrational numbers together are called as real numbers. The real numbers has the following sets of numbers as its subsets. Means we can say that all the natural numbers all the whole numbers, all integers, all rational numbers, as well as all the irrational numbers are real numbers. So here we can say a note that in short, all the type of numbers which are stated above are real numbers. Now let us discuss the concepts which we are going to study in this chapter. The first concept which we are going to study is Euclid's division lemma and its applications. Euclid's division lemma is dealing with the division of two numbers, its quotient, remainder, and the relation between all those things. And we can use that Euclid's division lemma to find out HCF of two numbers, also to decide the types of different numbers. The second concept which we are going to study in this chapter is fundamental theorem of arithmetic, which deals with prime factorization of the given positive integers, by using which we are going to find out LCM and HCF of two numbers, and also we are going to establish a relationship between LCM and HCF. The third concept which we are going to study is irrational numbers. Here we are going to prove that numbers like square root 2, square root 3, square root 5, square root 7, how they are irrational by using indirect method of proof. And the last part of this chapter is rational numbers and their decimal expansions. Here we will be able to state whether a given rational number has terminating decimal expansion or non-terminating recurring decimal expansion by using prime factorization. Now let us start with the first concept of this chapter, that is Euclid's division lemma. Lemma is a property or a statement which is already proved. To understand what exactly is Euclid's division lemma, let us consider a simple example. Suppose we are dividing 217 by 5, then by using long division method we can do the division in the following way. When we divide 217 by 5, the quotient will come 43 and remainder will come 2. Okay. Now here 217 is called as dividend, 5 is called as divisor, 43 is called as quotient, while 2 is called as remainder in this division. Now we know the relation between all these numbers. From this example, clearly we can say that 217 can be obtained by multiplying 5 to 43 and adding 2 in it. That is, 217 is nothing but dividend in this example, which can be obtained by multiplying divisor to quotient and adding remainder to it. So from this example we can say that dividend is equal to divisor into quotient plus remainder. That is, if we say suppose dividend is A, divisor is B, quotient is Q and remainder is R, we can say that A is equal to B into Q plus R, which is half of the Euclid's division lemma. And we know that in the same way, if we divide any positive integer by some other positive integer, that both the integers are going to satisfy the same relation, that is dividend is equal to divisor into quotient plus remainder. Now just remember that henceforth we are going to use A for dividend, B for divisor, Q for quotient and R for remainder. Now let us see the remaining half part of the Euclid's division lemma. That is nothing but condition on the remainder. To understand the condition on the remainder, let us consider the following example. The following table is going to help us to understand the condition on the remainder in Euclid's division lemma. Suppose we consider different dividends like 20, 21, 22, 23, 24 and 25. In this example, we are going to keep the same divisor, that is 4. And if we divide 20, 21, 22, 23 and 24 with 4, we are going to obtain the quotients as follows as well as the remainders. In this table, we can see that quotients are different, but the values of remainder are repeating. When we divide 20 by 4, quotient will come 5 and remainder 0. When we divide 21 by 4, quotient will be 5 and remainder 1. When we divide 22 by 4, quotient will be 5 and remainder 2. When we divide 23 by 4, in this case, quotient comes 5 and remainder is 3. Again, in the same way, when we do it 24 onwards, the remainders will start repeating. That is, if we divide 24 by 4, quotient will come 6 and remainder 0. Similarly, if we divide 25 by 4, quotient will be 6 and remainder will be 1. So here we can see that a particular pattern of remainders is continuously repeating. That is, when we divide any numbers by 4, the remainders are coming 0, 1, 2, 3, 4. That is, the lowest possible value of remainder is 0 when a particular number is divisible by 4, and the highest possible value of remainder is 1 less than divisor. Now, from above example, we can understand that when any positive integer a is divided by some other positive integer b, the remainder r is always greater than or equal to 0, but it cannot be greater than the divisor b. That is, the lowest possible value of remainder is 0 and highest possible value of remainder is 1 less than divisor. That is, the condition on remainder in Euclid's division lemma can be given by 0 is less than or equal to r is strictly less than b, which means the possible value of remainder can be 0 or more than 0, but it will be 1 less than divisor. So combining these two things, we can state Euclid's division lemma as follows. Euclid's division lemma states that for any two positive integers a and b, there exist two more positive integers q and r such that a is equal to b into q plus r, where 0 is less than or equal to r is strictly less than b. Means in this case, suppose in above example, instead of taking divisor as 4, if we take divisor as 5, the possible remainders will be 0, 1, 2, 3 and 4. Similarly, as we are going to change the divisor, the possible values of remainder will be also changing. Now, we are going to study some applications of Euclid's division lemma. To find out, the first application of Euclid's division lemma is to find out HF of the given numbers. Doesn't matter whether there are 2 numbers or 3 numbers. The process of finding HF of the given numbers by using Euclid's division lemma is called as Euclid's division algorithm. Means whatever process we are going to follow to find out HF of 2 numbers by again and again applying Euclid's division lemma till we get remainder 0 is called as Euclid's division algorithm. To find out HF of 2 numbers, let us say a and b, where a is greater number than b, we are going to follow the following procedure. Just see, we are just considering 2 numbers, positive integers a and b. We will see how are we going to find out HF of these 2 numbers by using Euclid's division algorithm. The step 1, first of all, we are going to compare numbers. We already have considered that a is the greater number than b. So we are going to apply Euclid's division lemma on these 2 positive integers a and b. That is, we are going to divide a by b. That is, we will divide greater number by smaller number. After division, we will get some quotient and remainder. Then by using Euclid's division lemma, it can be written as a is equal to b into some quotient q plus some remainder r. In this case, if remainder is equal to 0, then HF of the given 2 numbers a and b is equal to b, where b is the divisor of the step where remainder is 0. Remember that HF of 2 numbers is the divisor where remainder has come 0. Next step. Now in this case, if remainder is not equal to 0, if remainder is not equal to 0, then once again we are going to apply Euclid's division lemma on the b and r, where b is divisor of the previous step and r is the remainder of the previous step. So again applying Euclid's division lemma, we will get b is equal to r into some quotient q dash plus some remainder r dash. Remember that b is the divisor of the previous step and r is the remainder of the previous step. We have obtained new quotient q dash and new remainder r dash. In this case, if new remainder r dash is equal to 0, then divisor of this step, that is r, will become HCF of the given two numbers, that is a and b, and also it will be HCF of b as well as r. But in this case, if remainder is not equal to 0, that is if r dash is not equal to 0, then we have to continue this procedure. Then again we are going to apply Euclid's division lemma on the divisor and remainder of the previous step, that is r and r dash, and we will keep on doing the same procedure unless and until we'll get remainder 0. Last step, the HCF of given numbers is the divisor of the step where remainder comes 0. So remember that we are going to apply Euclid's division lemma again and again until we get remainder 0, and the step where remainder has come 0, divisor of that step is nothing but HCF of the given two numbers. Let us see some examples of finding HCF of the given numbers by using Euclid's division algorithm. Here we have the question. Question is, find HCF of the following pairs of numbers using Euclid's division algorithm. The first question is to find out HCF of 495 and 135 by using Euclid's division algorithm. Let us see how to solve this, how to find out HCF of these numbers by using Euclid's division algorithm. Answer of this one, the first step to get the answer is to compare the numbers. We will compare the numbers. 495 is clearly greater than 135. Why this is required? Because greater number among between given two we are going to consider as dividend, and smaller number we are going to take as divisor. So we will take A as 495 and B as 135. So we will apply Euclid's division lemma on 495 and 135. We will use long division, that is we will divide 495 by 135. We will find out quotient and remainder. We are not interested to find the answer in terms of decimals, remember it. So doing the long division, we will find that quotient is 3 and remainder is 90. So we can write by using Euclid's division lemma, 495 is equal to 135 multiplied by 3 plus 90. That is, when we divide 495 by 135, quotient will come 3 and remainder will come 90. Very important thing here is you have to write the numbers at the proper place. Means the dividend should be at its place. Then you have to write divisor, that is 135. Then we will write quotient, divisor multiplied by quotient, plus we will write remainder. Okay, so this is the first step we will obtain by dividing 495 by 135. Here we see that remainder is not equal to 0, and if remainder is not equal to 0, once again we are going to apply Euclid's division lemma on the divisor of the previous step and remainder of the previous step. Means divisor of the previous step will become dividend, whereas remainder of the previous step will become divisor. So as remainder is not equal to 0, we will apply Euclid's division lemma on 135 and 90. That is, we will divide 135 by 90 by using long division. You see what remainder and quotient we will get there. Okay, so again this can be written as, when we will divide 135 and by 90, we will get quotient as 1 and remainder as 45. So this can be written as 135 is equal to 90 multiplied by 1 plus 45. Here 135 is our dividend, which was divisor of the previous step. 90 is our divisor, which was remainder of the previous step. Quotient has come 1 and remainder is 45. Once again you can see that remainder is not equal to 0. So once again we are going to apply Euclid's division lemma on 90 and 45. 90 is the divisor of the previous step, while 45 is the remainder of the previous step. So again, as remainder is not equal to 0, we will apply Euclid's division lemma on 90, divisor of the previous step, and 45, remainder of the previous step. So again, by doing long division, we will get 90 is equal to 45 multiplied by 2 plus 0. That is, 90 is clearly divisible by 45. Remember that here also you have to follow the sequence. That is, first of all you will be writing dividend, then divisor, then quotient and remainder. Okay, this is the sequence. So this is the step where remainder has come 0, and now we know that where remainder has come 0, the divisor of that step is nothing but HCF of the given two numbers. So as here remainder is equal to 0, HCF of the given two numbers 495 and 135 is equal to 45. And one more thing I would like to tell you, whenever you are going to find out HCF of two numbers by using Euclid's division algorithm, you have to write the answer in this way. So this is the standard way of writing the answer also, because this kind of questions they can ask you for 3 or 4 marks. Let us see a note. Remember that HCF of the given two numbers is the divisor of the step where remainder comes 0. So wherever we'll get remainder 0, divisor of that particular step is nothing but HCF of the given numbers. One more thing I would like to tell you, whenever we are going to find out HCF of 3 or more numbers by using Euclid's division algorithm, what procedure are we going to follow? Suppose we are going to find out HCF of 3 numbers by using Euclid's division algorithm. In that case, first of all, what we will do, we will find out HCF of 2 biggest numbers. 2 bigger numbers we will select. We will find out HCF of those 2 numbers by using Euclid's division algorithm. Then whatever answer will come, whatever HCF of those 2 numbers will come, and the third number which is left, we will once again find out HCF of third number and answer of HCF of first 2 numbers by using Euclid's division algorithm. And again, by using this Euclid's division algorithm, whatever answer will come, that is nothing but the HCF of given 3 numbers. I'll give you questions like that in homework. We will see it later on. Let us take one more example of finding HCF of the given 2 numbers by using Euclid's division algorithm. Let us see once again how to find out HCF of 420 and 298 by using Euclid's division algorithm. We are going to follow the same set of steps which we have already done in the previous example. First of all, we will compare the numbers. Clearly 420 is greater than 298. So here the greater number 420 we are going to consider as dividend, and smaller number 298 we are going to take as divisor. So our first step, we are going to apply Euclid's division lemma on 420 and 298. That is, we will divide 420 by 298. We will see what quotient and remainder comes. We will get it like this: 420 is equal to 298 into 1 plus 122. That is, quotient will come 1, and remainder will come 122. So clearly here we can see that remainder is not equal to 0. When remainder is not equal to 0, once again we are going to apply Euclid's division lemma on divisor and remainder of the previous step. That is, we are going to apply Euclid's division lemma on 298, which is divisor of the previous step, and 122, which is remainder of the previous step, because remainder is not equal to 0. So again, by using long division, 298 can be written as 122 into 2 plus 54. Here, do not forget to follow the sequence, that is, A is equal to B into Q plus R. First of all dividend, then divisor, quotient, remainder. So we will get 298 is equal to 122 into 2 plus 54. Here 2 is quotient, 54 is remainder. Once again, that remainder is not equal to 0. So as remainder is not equal to 0, we are going to apply Euclid's division lemma on 122 and 54, which are divisor and remainder of the previous step. So again, by using long division, we can write it like this: 122 is equal to 54 into 2 plus 14. Here, when we'll divide 122 by 54, quotient will come 2 and remainder will come 14. Again, we can see that remainder is not equal to 0. As remainder is not equal to 0, we are once again going to apply Euclid's division lemma on 54 and 14. So when we'll apply Euclid's division lemma on 54 and 14, that is, we are going to divide 54 by 14. After that, we will get quotient as 3, remainder as 12. So we can rewrite that as 54 is equal to 14 multiplied by 3 plus 12. Again, we can see that remainder is still not equal to 0. So once again, we are going to apply Euclid's division lemma on 14, which is divisor of the previous step, and 12, which is remainder of the previous step. So again, by using long division, we will get 14 is equal to 12 into 1 plus 2. Here 12 is divisor, 1 is quotient, 2 is remainder. That sequence we have to follow properly. Once again, here we see that remainder is not equal to 0 yet. So again, we are going to apply Euclid's division lemma on 12 and 2. So again, by using long division, we will get 12 is equal to 2 into 6 plus 0, because 12 is a multiple of 2. Here again, do not forget to follow the sequence properly. Here 12 is dividend, 2 is divisor, that's why I have written 2 first. Then 6 is quotient, that's why 2 into 6 quotient is written in its place, and plus remainder, that is 0, because 12 is divisible by 2. Now here we have got remainder is equal to 0, and we know that whenever remainder will come 0, divisor of that step is HCF of the given two numbers. So HCF of 420 and 298 is equal to 2. I hope you understood this. Okay, it is very easy to do. If you practice some examples, you will easily able to do this one. With this, I would like to tell a note to you. Some of the times they will ask you to show that by using Euclid's division algorithm, they will ask you to check whether the given pair of numbers are co-prime or not. So we'll see what are co-prime or relatively prime numbers. Two numbers are said to be co-prime or relatively prime if their HCF is 1. So whenever they will be asking you to check whether the given pair of numbers are co-prime or not, you will find out their HCF by using Euclid's division algorithm. If HCF comes 1, you will write as they are co-prime. If it doesn't come 1, you will write that they are not co-prime. Now, some questions for homework. The first question I have given to find out HCF of the following pair of numbers. There are 20 pairs which are given to you, where you have to find out HCF of all these numbers by using Euclid's division algorithm. The second question I have given, by using Euclid's division algorithm, you have to check whether the given pair of numbers are co-prime or not. Means again, by using the same method, we will find out HCF first. If that HCF is coming 1, we will write as the given pair of numbers are co-prime or relatively prime, and if it doesn't come 1, we will write they are not co-prime. The third question I have given to find out HCF of 3 numbers together.